Okay, I think we can start. Hi, everyone. So this is a talk. Well, you guys have been hearing about capture checking since yesterday, and this is the third talk of today about capture checking already. So I don't think we need an introduction into capture checking anymore. So I'm Nguyen. I'm a PhD student at LAMP. Uh, I did a lot of stuff in concurrency stuff in Scala. So I wrote Gears. That was when I spent most of the time, at least last year. And this year, it's more about integrating capture checking into Gears itself, and then it all comes back to like the entire thing, like the standard library and everything. So I have a little bit of experience putting captures into existing code. So, okay, so this talk is a little bit different from the others. I will have quiz, and I'm gonna grade everyone. And so we're going through a little bit of, are we capture checking yet? We're going through a little bit of the collections library, some of the new stuff we have in Scala 3, as well as some of the small stuff that we have built over time, just to see that what kinds of more convenient Scala we can build with capture checking. And also, maybe coming out of this talk will be some kind of guidelines about how to integrate capture sets into your own library as well. But I expect this to be mostly like a rant about everything. Okay, so let's start. This is my version of the Scala stairs. With the capture checking, it's everything is a work in progress, but it's solid. It's solid. And so what's the state of CC right now? Compiler is there. Capture checking is working on the nightlies. You can grab the nightlies on nightly.scalalang.org and following the guide from Oliver and from Martin before. And you can also follow the QR code, which will lead you to the repo that Oliver mentioned earlier with the SBT setup so that you can get the latest nightly. And also the documentation is there as well, so everything is good for the compiler. And what can we do already? So every example in Nicola's and in Oliver's talk and also in Martin's talk as well, they all compile with the current compiler. Plus, we have separate compilation. So that means if you have something with capture checking and you want to use it with something that doesn't, it's mostly work out. However, it's not that great, right? So you have a file a.scala that defines your width file. I think you've seen this like 1,000 times already. I don't need to tell you what it has. And then you start with B, right? And you turn CC on, everything works. But then you try it with identity, which is like the canonical Evo example. And yeah, everything still compiles. That's kind of bad, isn't it? So in a sense, separate compilation lets you do things, things compile. But to ensure safety, ideally both sides should be capture checked. And so that creates a problem, right? Because we have a compiler, we have the language that is capture checked, but if we don't have libraries that are capture checked, we can't use anything that is capture checked, then it's not really safe, isn't it? It's kind of like a toy. And so we have to start with the thing that everybody uses the most, right? So what's the most used Scala library? Well, it's the Scala library. And more specifically, it's the Scala's collections. The famous collections that everybody knows about. And I'm just gonna list some stuff about the collections here. Like it provides a generic implementation of collections for any kind of data. Most of them are strict, right? So you have lists, hash map, binary trees, array buffers. Sometimes they are lazy. So you have lazy lists or iterators or view. Those are things that if you do map filter, they don't really do anything, just capture the whole thing and then run them when you ask them, right? And it's organized into a hierarchy, and it's mostly dependent on subtyping or subclassing. So here I'm listing two of the dependency chains. You start with iterables most of the time, and it goes to seek and index seek and immutable seek and then immutable list. And most things are going that in that kind of direction. And so, in a sense, we can do collection polymorphism by just taking like supertypes, right? So, if you want to take most kinds of collections, you can write a function that takes an iterable. That makes sense, right? Most things you can pass in as iterables. And finally, in the implementation of the standard of the collections library itself, we share code by having common traits, right? So map and map view are mostly the same. Most of the methods are the same, so we share most of the implementations in something called map ops, which is a huge thing with 4 type parameters, one of them higher order. So if you have seen them, they look kind of hairy. If you haven't seen them, please have a look. Okay, so there are a few things that make collections easy and hard to capture check. And the first thing is, because everything is like so generic, one special thing about the collections library is that most of the time, like 99.9% of the time, every type variable you have it has no constraints, right? So boxing actually works out in a lot of cases. So here's an example, right? Files again. You have a function taking a file. It has a cap, so you know it's tracked. You put that into a list. So at this point, assume that we don't have capture check library, standard library yet. And so we put it in the list and try to do a filter, right? Just filter that the file size is larger than 0. And if you look at the type of the list, well, we have file is capture polymorphic. It's tracked. List doesn't have a capture because we have boxing, as explained previously. But the type inside the list still retains the capture. That's a feature of the language. It's not a feature of the standard library. You don't have to capture check it. And if you take the file out of the list, it retains the capability. So everything is fine, mostly. Until you get into things like iterators, right? Iterators, they have a habit of forgetting because we haven't told the system that our implementations actually retains things. So in this case, you start with a list, you turn it into an iterator. The point of turning it into an iterator is just an iterator of ints. It's completely pure, right? And then you do a filter, and then you capture A, which is a file. But the implementation doesn't know because we haven't capture checked it yet. We haven't told it that the resulting iterator is going to capture something. And so we run into a problem because now this iterator is still pure, and now your program is having a problem. So this information is actually useful, right? There is a point to actually doing capture checking on the standard library, although many things work out of the box. And the fact that we want to add these things into the standard library is, I believe at this point we are convinced that they are useful. Okay, so how do we actually do it? It depends a lot on the user expectation of this subtyping as collection polymorphism, because as you can see, as you can kind of see, like the divide between things working and things not really working is whether the collection is really strict or lazy. So let's play the first quiz of the talk. What is the expected capture set of this function? So we have a function do filter that just takes an iterable and a predicate. Both of them can capture anything. And you just do the filter, right? Like take the iterable, call the filter on the predicate. What is the capture set of the returning iterable?
This?
Exactly. So I'm going to unfold the implementation here so we can actually see what's happening. We create a new iterator. It mentions XS in its val, and it mentions spread in its definition of has next. So it makes sense that, yeah, the implementation is going to capture both of them, right? Okay, next question. What is the expected capture set of this function? So this is the same function. It takes a list instead. It's exactly a Scala collection immutable list. Empty sets. Exactly. So again, I unfold the implementation. We just do a pattern matching, and yeah, we don't really capture anything, right? We call the predicate, we build the list, but we don't really capture anything. So in a sense, list is strict, so we don't capture anything. And list actually never captures anything because it's completely generic. Everything put into the list is boxed in the box sense of capture checking. So we can actually drop all the caps. Okay, how about this one? This one. The same thing, it's a seek instead.
You're cheating because seek is pretending to be strictly strong.
Who's the cheating one? Come on. All right, so I would guess that most people have an expectation that seek is somehow strict, right? But actually it's not. There's a sneaky little data structure called lazy list that actually extends seek. And yeah, it's not that hard to just do something bad with a lazy list. And yeah, I suppose I should have made some people angry about knowing this fact. Now your life is ruined because you don't know whether your seek is lazy or strict anymore. It's an unfortunate fact, but so here is kind of like the basic view of the zoo of base collection types that I have written down and tried to capture check. Well, I have capture checked all of them, but these are the interesting ones. So I divide them into strict and lazy, right? Strict is the one on the left with the, oh my God, I put them like bright orange and dark orange. Okay, but you can see which one is strict and which one is pure, right? And then in the middle, we have the common implementation. So MapOps actually provides the implementation for both map and map view. One of them is strict, the other is pure. One of them is strict, the other is lazy. And the same thing happens for seek-op, which provides an implementation for both seek and seek view. And so the ops themselves have to have a possibly lazy interface, while the same thing in map should have a strict interface. And then there's the lazy list, which in our efforts, we think it's better to just give up, deprecate lazy list, and introduce something else called lazy list iterable, where it doesn't extend seek, and so you can kind of like be happy now, be relieved. Okay, so it's kind of a pain, right? So you have users' expectation and you have to adjust accordingly. Like it's not always like the best option here for us to make the standard library sound is to make seek possibly lazy instead, and then we can capture everything. But it goes against everyone's expectation, right? And being lazy itself, because of all the additional captures, it actually makes everyone's life worse. So I guess that's a rant. Let's go to the next thing. I said that I would recommend people to read the ops implementation, but I'm gonna give you one. So here is another design question. So this is zip, right? It's a method of iterable ops, so iterable will use it. It takes an iterable once. You give it some capture set, and it returns some capture set, right? What should you put there? Like, what do you want to put there? So there are two parts to a question, like what capture set should you put for that, and what capture set you should put for the return.
Should that be polymorphic, some C hat in the type parameters? We say some polymorphic capture set. I don't know what it is, just put it in the variable.
Right, so we agree that that should be capture polymorphic, so we put a hat there. Okay, so we put hat. Right, so I think it's fine and common to for everyone to think that, oh yeah, iterable ones, it can be anything, including an iterator that captures all your functions. So yeah, we should take everything and reflect that fact. So that should take a hat, and the return type should take this and that. Okay, what about this one? So same trait, the function is now unzip. So what unzip does is it takes, well, this iterable and then implicitly a function that turns an A into a pair, and then it turns the whole thing into two sequences. So the question now is more like, it's not exactly what you can take, but what you want to take. Would you want to have an implicit functions that implicitly captures things? Perhaps not, right? And so in this case, personally, I would prefer to have my as-pair function to be pure, and the resulting iterable, because it's still an iterable, it should still capture the old ones. Of course, if you really want your function to be impure, we have something for that. It doesn't take the function implicitly. Okay, now this is a real question. So we have this thing that takes an iterator and turns it into a Java iterator. So Java things are untracked because we can't put capture check into Java, unfortunately. So we can't put a capture set on iterator. So what should we put for our own iterator instead? Well, it should be empty, right? Because you return something that's untracked. So to be safe, you should, of course, like force your iterator input to be untracked as well.
If you're interacting with Java, surely you're fine dropping this integration because you know you're going into unsafe territory.
Right, and so I think it's a little bit better to push this a little bit to the user themselves. So at this point, the users always have two options, right? They can construct the thing purely by construction, like the compiler can prove it, or they can go trust me, bro, and do unsafe assume pure. Okay, so I put bold on the exclamation marks, but I don't think everyone can see it. So that's kind of sad, but be very careful about user expectation and about your own expectation as well. Okay, so the third thing about sharing common traits is something a little bit about maintaining backwards compatibility, right? So it's about claiming my purity, kind of. I have this iterable ops thing. It has a flat map. I have given you the capture set, so you don't have to guess this time. The point that I want to make is this flat map implementation actually is used by both seek and iterator. It's the exact same implementation, like it's the exact same override. If you go to Scala doc of the standard library, open up and see the implementation file, it will point to the same exact function. It's the same override, but it has different return types, right? One of them has no capture sets and the other has one. It's kind of interesting, isn't it? So there is a lot of things that we have to think about when we, especially for the standard library, when we do this porting, that we have to maintain like many levels of backwards compatibility, like source, so everything doesn't break, tasty, so everything doesn't break, and binary, where everything doesn't break. And so through a lot of careful choices, we end up with this thing called caps.pure, which first, it marks every instance of the class or trait to have no capture set. And then the compiler can assume this guarantee. And so, for example, in the same iterable factory, we have this from function. It takes iterable once and returns an CCA. So CC is the collection higher kind of type. You'll see a lot of them in the standard library. And it captures source by default because it is the factory of anything that is iterable. But when we instantiate CC with seek, the compiler knows that, yeah, every valid instance of CC is going to have no capture set. So yeah, putting a capture set on it is equivalent to none because it can't capture anything, even if you pessimistically assume. And so it's all good. And we have this from function that just returns a pure collection. And then we erase pure at erasure. So it's never a thing. So that's how we maintain all the levels of compatibility. And on the other side as well, where sometimes you want to prove your purity, sometimes you want to demand purity, right? So one of the cases in the standard library that we had was strict optimized seek ops, which, as the name says, if your seek ops is actually strict, then we have an optimized version for you. And we didn't have a bounds on this thing before, so I'm happy nothing went wrong. But now with capture checking, we can put a guarantee here that the collections built are always strict or pure, which is just an upper bound on caps.pure. And for backwards compatibility, we also turn off this bound when capture checking is turned off, which is, well, a little bit unfortunate because now your existing code, if you do try to extend strict optimize seek off where your seek is a lazy list copycat, then you're doomed. But you have always been doomed from the beginning. Yes. So yeah, that's my multiple part rant about porting the Scala collection. I think we took a lot of effort in to actually make this thing right, actually properly dividing this, the wall between strict and lazy, and we made it without breaking any levels of compatibility. So I think that was an achievement. And for the achievement, I'm gonna get you guys to do it. Let's practice capture checking. And to do capture checking, you all have to know the magic words. What is the magic words? Import language experimental capture checking. Okay, we're gonna do something not so easy but not so hard. This is iterable ops partition map. So what it does is it takes a function. So this is a collection CC that takes an element type A. It takes a function from A to either A1 or A2, and it does the partitioning, right? So it creates two collections, one for all the A1s and one for all the A2s. And what the implementation says is that it's going to create two views, one for the left-hand side, one for the right-hand side. It passed the same F. And then it's going to, in the implementation of the view, it's going to map and filter only the left side or the right side. And finally, we just call iterable factory.from, which is a function we just saw before, which just takes an iterable once and build a collection out of it. Note that we return the same collection type, but a different element type. some iterable ops is just a type alias for some kind of iterable ops. And let's run this capture checker. Voila! We have some errors. The error says expected pure iterable ops, but we have iterable ops capturing this. Where do we change the code? I'm gonna give you hints.
Should some iterable ops not have a CC parameter?
Yes?
Should some iterable ops not also have a CC parameter?
So some iterable ops is type alias for iterable ops of A, and then the CC type is like the highest type possible, so it's like iterable ops, and then like you don't need to care about it, yeah.
You annotate some iterable ops with the hat?
Yes, exactly. So here the problem is we are instantiating left partition mapped with something that it should not take, well, it doesn't accept right now, which is an impure sum iterable ops, because it was missing a hat. So let's add the hat. And we wave our magic wand again. We get new errors. This time, compiler says expected view A1, but we got view A1 capturing this and F on the right-hand side. What should we change? Yeah, exactly. We just yeah, we just update the type. Okay, but also we can just drop the entire type and let type inference does this thing. Okay, once again, now the compiler says expected CCA1 got CCA1 this F. Where do we change?
Return type.
Exactly. You guys are getting good at capture checking, you know? And one more time, and this time the compiler accepts. Good job, everyone. Okay, all fun aside, I think you've seen this table before. It's from our paper in Uppsala. This is kind of like a summary of how much we've changed the standard library, especially the collections library, actually, in order to make it capture check. So you can see that there are about 6,200 functions in the collections, and we changed about 700 of them. So that's like a little bit over 10%. And then most of the changes, like so the second and third line is only universal capture, so like only adding hats and only capture set on return types. So only annotating like, you know, this and F to the return types without changing anything inside the functions. So they add up to a lot. And yeah, also I want to say something about the total number of lines as well. Like the total number of lines in the collection code is about 32,000. And we changed only about 1,500 in total. So I think that is a reasonable amount, given that we changed 4 lines for this thing. That doesn't amount to a lot, isn't it? So I think it's low notational overhead. And, worth trying. And so back to our state of CC, we have the collections. It's actually not mostly compatible anymore. It's fully compatible now. And of course, like documentation is unlikely. Oliver has shown you that iterators have capture sets on the documentation, which means you can kind of trust it now. And let's talk about something else. Like I'm tired of collections. Scala 3 has this thing called boundary break, which Oliver have also mentioned. It's a replacement for non-local return. So in Scala 2, you have something that lets you return from like very non-local scope. And it looks kind of dangerous, so I never tried them. And every time I did a return by mistake, the compiler warns me, and I'm like, this sounds wrong. I'm scared. And yeah, the boundary break thing looks kind of like this. I think I messed up the indentation a little bit, but this is an implementation of find first. So takes a predicate, returns an option of the first thing it finds. It's reasonably capture checked. The collection is capture checked. We don't think about the boundary break for now, but the implementation says you start a boundary, and then you loop over the list. And then if the predicate matches, so if f item, then you just call boundary.break with some item, and that would immediately it will immediately stop everything from that point all the way up to the boundary and return the thing inside the break call. And of course, like if we did the for each successfully without breaking, then we just return none at the end. And also something to advertise, this boundary break actually compiles away into like low-level bytecode jumps if you don't have non-local returns. So you can use them as like normal break in other programming languages, but you can set your bound anywhere inside the function. But this one is not local. Okay, so let's unroll this a little bit. So I think everyone has seen boundary break, but maybe you haven't seen this extended version where we extend boundary into boundary.apply, and it takes a context function with a label, and it uses it somewhere in there in the break. And so we can think about this boundary as creating the label as a capability, right? It's a capability to break out of the boundary. And so capabilities, capture checking, you know the deal, right? We have this implementation right here. It's nothing too special. You can kind of implement this on your own, actually. Actually, this is a full implementation already, except for the runtime exception. You can put anything there. So break is an exception. It takes a label which marks which boundary it belongs to, and then the value itself. And inside apply, you just create a new label and then run the body with that label. And then if you happen to catch a break during that time, you just compare a label. If they match, you return the value of the break. Otherwise, you keep throwing. And that's pretty much the implementation in the standard library as well. But we have inside the compiler some work to turn them into jumps if they're local as well. So what can go wrong? Well, capabilities be damned if they leak. So this is some implementation of an iterator option, and you flip it into an option of iterator, and then you try to do the label thing, you map it, and then everything kind of breaks, right? Because if you take an iterator and you map it, it returns immediately, never calls the function. So yeah, we create a new iterator capturing the label, and at this point, calling next will crash the program. Nothing so fancy, I think. And so our task is to check that the label is not captured, or we capture check the label. Let's go back to the implementation. This time, I'm going to go use a fancy thing called extends cap.control. Caps.control is it's basically just a subtype of caps.shared capabilities, which you have seen before. So essentially, it just marks this thing as an impure reference or like a root capture every time it is created and referenced. So exactly in these 4 places. So the first 3, you can think about it as always having a cap afterwards. And in the inference type of local, it also has a hat. And so control is specifically for things that affect control flows. It's gonna be relevant later, but later as in like in the future, not later in the talk. So don't worry about it too much. Okay, so That's it. Let's try waving the magic wand, and then we can do it together. Wait, it's done. It's done. We capture checked it. Yeah. If you wave the magic wand on the wrong function, yeah, you catch the error. It's that easy. It's that easy. And why is it not error? Why is it an actual error that you can't escape out? Is because you have to give the boundary a type iterator t, but this iterator is gonna capture the label, but the label comes after the type, so you can't name it. So the only thing you can put there is a cap, whereas with boxing, you already know that you can't box, you can't unbox a cap, so it's impossible. And so yeah, boundary is in the standard library. It's a one-line chain, so why not, right? And we also have other things cooking in the standard library as well, like futures and try, other control flow stuff. But they're still in the work because the other two, as you have known, it's merged at like 1:30 this morning. So I wish I had time for more. Okay, so let's talk about something completely different. Like, we're not talking about the standard library now. I'm tired. Let's write our own thing. So Rust has this thing called results, which is kind of really interesting. It's basically just an either, but it's built specifically for error handling. And so, you know, unlike either, which is kind of like an OR type with attack, result is really like there's an error case and an OK case. And we built it as part of steps, just small collections of random things that we think would make Scala more convenient, but not ready yet to put into the standard library. And it provides a convenient syntax for error propagation. It's built with boundary break, and it's gonna steal some of Rust stuff. So this is kind of like a small example, right? Maybe you've seen this before because it was mentioned in Martin's talk already, but here it's also kind of the same deal. We have the results scope, which inside the results, you can call OK on any results that has the same error type, and it will unwrap the results if it's an OK, so you get the real thing back. If it's an error, it will just abandon everything and then throw the error back into the result scope. Okay, I wrote it in my slides. Okay, so with the same extension, you can see like, oh, there's also a label, and we use it every time we call OK. So it's kind of like the same deal, right? Label is recoverability, consequence be damned if leak. It's the same function. I did the same thing. And what does it take to capture check result this time? Nothing. Yeah, I didn't change anything. I did the magic one, right? Import language experimental capture checking, it just works. And please try using it. We have a very nice version of OK where we actually allow you to do a conversion of the error types if you provide the conversion instances. So it's kind of more like with the Rust question mark operator. And we also have like all the conversion from seek option either and other functional stuff. So it's all there. I think we don't have a lot of time left, right?
You don't have any time left.
Oh, I don't have any time left. I miss my gears. Let's speed run through gears, right? Gears is a thing about concurrency that I gave a talk about this at Scala last year. And to be honest, I didn't make a lot of progress on it because I was trying to capture check it, and it took so much of my time. But it's kind of, in a sense, it's kind of like the same deal, right? You have an async context, it threads down, and then you call it everywhere, and you don't want it to leak. But this time, you can spawn futures as well, and futures can capture things. The big deal with future is just that while you have an async context, you can await for futures. So they kind of compose with other scope things. So here I'm spawning future, and inside I have a result, and then I'm calling OK in a bunch of places. it kind of works, and we're erasing things, we're mixing stuff. But there's one thing that you don't want to do, right? Like if you have a result and then a future inside, then the future, even if it reaches an error by the boundary break rules, it creates an exception and it throws to nowhere because the future might run on a different thread. It's a pain. So with the capture check version of Gears, you wave the magic wand and this thing will give you an error because the future is capturing the label. And it's kind of pretty much it, actually. Like the trick is just you capture the body as part of the future as well. So yeah. Sometimes difficult things aren't difficult. It's that easy. So yeah, I was going to let you guys do the await all as well, so you can get used to some capture variables, but I think we don't have time for that, so I'm just going to walk you through, and then it's just also not a lot of changes. This await all takes a seek of futures, and then it kind of just await for all of them. In a single future, it will capture the same thing as everything inside a seek. So you have to have a way to talk about things inside a seek. And so you need a variable. But yeah, I think that's kind of like the meat of my talk. And it was just, most of the rant is just about things can be hard, especially if you're doing fundamental things. But once the fundamental is done, you can see that maybe it's not that difficult to start capture checking. And you can try out the nightly right now. Separate compilation really got you, so you can just call the magic word on file by file, and everything else not capture checked should work fine. We only add annotations to your tasty, so compiling should not be a problem. It takes a little bit of time to get used to the capture set, but everyone's getting there, right? We did our maybe first capture checking, and it's not something entirely trivial as well. Also, the compiler messages can get hairy sometimes. I don't put one here, but you've seen one before. Yeah, please try do it. Post your results, tag Scala, and happy writing capture check Scala. Yes, I'll be happy to take questions as well. Yes.
What impact does this have on the compile time of the standard library? Does it take more time to compile that?
So we have this benchmark in our OOPSLA paper. I don't remember the exact numbers, but it's minimal compared to the actual typer, right? So not that much of an impact.
I think it was 15.
Yeah, 15% of the typer. Yeah.
15% of compile time.
Oh, okay, so it's 15% of the compile time, which is a thing. Okay, okay, now it's a thing. Okay, it's a thing. Yes.
Will there be backward compatibility to libraries not using the standard library capture?
So, as I said, everything we add into the standard library as of right now is lazy list iterable and annotations. Like, so there are annotations everywhere in the collections and boundary and some other things, but there are annotations. And if you don't have capture checking turned on, the annotations have no semantic meanings.
But if they are turned on, but I'm using a library that is...
So it's like the other way around. If you turn on CC with the unchecked standard library, you run into like the iterator problem that I've shown you. Well, that's the nature of things, right? You can't turn capture checking on things that aren't capture checked.
Basically, if something is not capture checked, then it will just replace all possible captures with wildcards which are compatible with anything. So it lets it compile, it's optimistic, but it possibly won't find errors that it would find if it was capture checked.
Yes, I think you have your hands.
So just from my understanding, you sometimes reference these sort of named capabilities in the CAPS
Yes.
So you have caps.async and caps.pure and
Ah, yes.
like that.
Yes.
What exactly differentiates those, and are there some kind of implementation to that, or is that some kind of magic?
Right. I mean, we can go through this one by one, but there aren't so many of them. So we have this capability classifiers. So right now there is shared and exclusive. You have seen it in Oliver's talk, right? So all those things are classifiers that includes control. Pure is a different thing. Pure, if you look at the definition of pure, it only is an empty trait with a self and an arrow, and that's it. What it does in capture checking is that the capture checker looks at the self and it sees that the self type doesn't have a capture set. So it means the upper bound of the type, upper bound of the capture set of the type is empty. That means every instance has to have an empty capture set. That's the semantic meaning when you turn capture checking on. It also has this optimization-ish thing where at erasure, we will erase away the pure. So you can't check it at runtime, but you don't pay anything for adding pure to your types. And also, as I said, if you put it in the bounds, it will be ignored when capture checking is turned off for other people. Yeah.
I had a general impression when we were going through examples and trying to make things compile.
Yes.
That often adding this hat mark would fix things. So I wonder, would it be similar to a situation that occurred when Java introduced check exceptions? So when developers in a hurry wanting to get tasks done simply caught the exceptions and ignore them or rewrote them as runtime exceptions.
Right.
Would you expect the same happening for Scala? Everybody in rush just adding the hats?
So I think there's a little bit of a difference. Like you can catch every exception and then ignore them. You can't catch the hat and then ignore them. Well, you can with unsafe, but unsafe is unsafe, right? You can add hats to everything, but as I have said, it's kind of like a trade-off between what your users want, what you want, and what the system can do. The system can accept everything as hats, but then your trade-off is everything has a capture set now. You have to trace everything, right? It's in a lot of cases that's not what you want, right? If you have a list of totally generic things, you don't want them to have capture sets, right? Yeah. So it's I think we have the system, and it's it allows you to opt in a sense that you can turn on the hats where you want, and it's kind of like a taste and a design problem now, right? So it's a thing that we will continuously experiment, but I think it's a okay ask for everyone to try it out and find your own comfortable area of like how much capture checking you would want in your types.